All right, so welcome back to ENGG1300. We're in week 2 now. So today we'll be talking about moments. Essentially, that'll be the main focus of today. But first there's a couple of housekeeping things I want to talk about. One sec, just checking. Oops, what is going on? The record. Okay. All right. Okay, so your design project just got released. This will be worth 30% of your course grade, and it'll be due in week 11. So you've got a lot of time to do it, and as a matter of fact, you don't have all the knowledge yet in order to solve the assignment. We'll cover how to solve a truss in week 4, and then you can solve most of the problem. And then it won't be until week 7 or 8 where you'll learn the skills to do the dynamic equivalent load, which is a small part of it as well. So probably by week 8 you can solve the whole thing. But yeah, in case you haven't seen it, I would recommend that you give it a proper read. But in summary, the way that it works is you're going to produce a report up to 20 pages, and then there's some pretty specific formatting rules that are on the first page. And it gives you a pretty extensive list of things that you should cover when you're writing, and a little bit of a timeline so that you're on track, I guess. What will happen is that we will cover in the class. I haven't figured out which week I want to do this in, maybe week 5 or something like that, once you guys have learned trusses, on how to solve an example case. But this first one is just a demonstration case, so I'll be covering that in class. And then when you scroll down, you can see that there's going to be 4 options that you can choose between. So option 1, some kind of scaffolding system. Option 2, some kind of plane truss for a helipad or whatever. Option 3 is a small crane of some sort. Option 4 is an elevator work platform. And yeah, they give you a bunch of material properties to work with. And you'll also be doing a space gas analysis. Well, they recommend that you use space gas, but you are allowed to use, I believe, any structural solving software that you would like, as long as you properly reference how you did it in the report. And then you'll also do a quick axial stress check, which we'll talk about later as well. Yeah, anyway, so that's pretty much the assignment. There's also a marking criteria, which you should probably give a good read as well, so that you can make sure you get all the marks you can. So that's the mini design project. Do you guys have any questions about that right off the bat or anything? If not, that's all right, because it's not due for a while and you have plenty of time to do it. So yeah, that's the first that's the first thing I wanted to talk about. The other thing I want to talk about is I wanted to promote these PASS sessions. So PASS stands for Peer-Assisted Learning Sessions. I used to do these back in the day when I was a demonstrator for ENGG1300, but before I was a demonstrator for ENGG1300, I was running these PASS sessions. So undergraduate students run these basically, and they're just drop-in sessions. You can just go there and ask questions about the course and how to do questions and stuff like that, and you get some student mentors who are probably 3rd or 4th years to help you out. And as a matter of fact, I taught both of these students, so Gia and Evelyn. Evelyn was in my 2023 class, and Gia was in my 2024 class when I did demonstrations back in the day. So yeah, go support them. Yeah, anyway, so that's on the Moodle forums, I believe Wei has promoted that. Okay, so that's that. All right, so we'll get on with the workshop. Just checking I'm on the right document. Okay. So yeah, basically we're going to be talking about moments today primarily, but I want to give you guys a bit of context before that in terms of this concept of bodies/objects, right? So before we get to that, actually, I forgot that I usually chuck the course structure on the first page. So just to give a recap of where we're at and where we're going. We're still talking about statics for now, and we're focusing on the second important component of basics that you want to learn in this course, which is moments. So last week we talked about forces. Now we're going to learn about moments. and in the following weeks you'll learn about structures. So in terms of your first block test, that will be week 3 Saturday, so next week. And I've been told by Wei that, pretty much only these 2 weeks of content will be in that block test, but I think I'm still going to cover beams next week because it's important, and it'll be in the following block test. And what you'll find if you do decide to attend that workshop is that a lot of the concepts can still be applied to your first block test, just not in the same, just not explicitly. Anyway, so I think it's still worth for you to come to this workshop next week because you'll find that if you learn about beams, you'll learn more about forces and moments that you didn't know before. Anyway. So yeah, that's that. All right, let's talk about bodies and objects, okay? So this is a rather abstract concept, and it's something that you've probably been learning in physics/engineering studies, but you haven't quite been able to put your finger on what you actually talked about. At least that was the case for me, right? So the idea is that you can think of physical objects as this idea of a body, where you can look at it in terms of its dimensionality. So this idea of a particle is a physical body that you treat as 0-dimensional, so it's a single point in space. And then kind of a step more complex than that are rigid bodies and flexible bodies. Now in this course, we don't really deal with flexible bodies, we deal with this idea of rigid bodies. And the difference between these 2 things, essentially, is how you treat deformation. So just imagine you're doing calculations on a steel beam. You consider that object as rigid when you're doing your static analysis. All right, so essentially it doesn't deform and do all this weird complex behavior. But if you were to deal with a flexible body, think instead of that beam, it's made out of marshmallows or spaghetti or something like that, where it can warp if you apply loads to it, then that, as you can imagine, could get more complicated, right? Anyway, so with all that said, essentially we'll be dealing with particles and rigid bodies in this course, and these words aren't explicitly really said to you until the second half of the course, where we're talking about dynamics. We're going to talk about particle dynamics and rigid body dynamics, but in terms of physics overall and engineering mechanics overall, we still talk about these concepts in statics. We just don't explicitly say these words, all right? One sec. I'm just going to check if we can turn the aircon on or something. It's kind of stuffy. Okay, hopefully that turns on after a while. Okay, so in terms of the dimensions, right, you can see here, you can think of rigid bodies in terms of 1D, 2D, or 3D. And I'll give you an example of some ways you can treat these, right? So basically, when we talk about beams and stuff like we will today, this is actually a 1-dimensional rigid body, at least the way that we deal with it in terms of static analysis. So a beam is a 1-dimensional rigid body, right? And for a 2D example, you might think of something. Actually, you'll see this in the practice papers for your first block test, but there'll be some kind of frame of some sort, for example. And once you start treating this structure in terms of multiple dimensions, to just unplug. Let me just check my recording is not busted. It might have frozen. One sec. Oh, hello. That's me. Okay, whatever. We'll just do this view. Is it frozen? Yeah, one sec. There's always issues with the recording if the thing unplugs briefly. Okay, I think it's working now. I'm waving. Okay, it's working. All right. Sorry. All right, so yeah, anyway. So point is, if you have to consider multiple dimensions, like for this frame, we're working in 2-dimensional space, right? So this will be important. You'll see examples of this throughout. Oh, it did not fire out. Sorry. Let me just double check the recording hasn't broken. Okay, I'm waving. The mouse is moving. Okay. And you guys still can't see it. Fuck. Okay, give me 1 sec. I'm gonna try something. I thought they might have fixed this because this was an issue last week as well. In this room, that is. Hello? Okay, great. All right, that's working now. Okay, sorry about that. All right, so we're back. So yeah, anyway, 2D frame, right? You're considering multiple dimensions, so like in the X and Y axes, for example. And yeah, 3D cases will not particularly be focusing on in this course, but you know, that would be a lot of structures in real life where we're dealing with three-dimensional space, X, Y, Z. Yeah, point is, this course will mostly focus on these things. Okay, any questions so far? All right, so this is just the space that we're operating in, okay? So it's good to keep in mind when we see the following stuff. Checking I'm on the right document, okay. So let's talk about moments, all right? So this is one step more complicated than forces, right? And there's a few lenses which you can view moments from, right? The different types of moments there are, the formula that's associated with moments, and directionality. Is that a word? Yeah, I don't know. Okay, so in terms of different types, I want to differentiate between bending moment and torsional moment. Okay, so essentially when you've got something like a beam, like this, and you've got these moments being applied onto it, it will basically deform the beam such that it sags like this. And yeah, that's the deformed shape, but the idea is that you're applying a bending moment to the beam. Actually, this is probably not even the most simple example I could give you. If I show you another beam, and instead we've got, let's just say, a force in the middle, okay? The idea is, yeah, you'd also see this kind of deformed shape that looks like this. And we're gonna, we apply a bending moment to it, all right? So the system's bending. And the important thing to note is this kind of black dashed line that I've drawn, which just represents, let's call it the longitudinal axis, which is kind of the direction of length, I guess, of the beam, so it's longest dimension, right? And yeah, the bending happens relative to that. The other thing to note is there's something called a torsional moment, which is if you instead imagine that longitudinal axis, right? Let's call that L, on a similar beam or long object, long, roughly one-dimensional object, and then you twist it relative to that axis, that's called a torsional moment, okay? Or torque being applied to it, right? So yeah, just keep in mind this imaginary axis called the longitudinal axis that runs through your beam. It's not imaginary, but yeah, like just visualize this longitudinal axis that runs through your beam or whatever structural member, and then moments that are applied to it, think of them as bending moments or torsional moments, depending on how that twisting or bending happens, okay? Okay, next thing is the formula that's associated, right? So you've got your induced moment, and it's got a few different sets of units that you might see, such as kilonewton meters or Newton millimeters. You can also see, if you're working in SI units, I guess, Newton meters, all right? The idea is that this value comes from a force multiplied, cross product specifically, with a lever arm. I'll explain the lever arm concept a bit more thoroughly later, but just to give you a simple example, let's say we've got a bolt with a nut on it, and we've got like a wrench or something. You have to think of it like that longitudinal axis runs in and out of the page of that nut, and say we've got a force like this with a lever arm like this. Okay, so the lever arm is a perpendicular distance from that force to our point of rotation. And that has an induced moment, right, like this. And specifically, that's a torsional moment, right, in this case, so torque. So it's twisting about that axis. Yeah, does that kind of make sense? Okay, that's an example. All right, anyway, so the idea is that these moments have a direction associated with it when we're analyzing it in 2D, essentially. So how we analyze it using pen and paper, basically, on a page. You can think of the moments as going counterclockwise or clockwise, right? So for example, that example I was drawing earlier with the wrench, that moment, that torque is being applied clockwise, right? So that way, relative to our point of rotation. And conventionally, we use counterclockwise as the positive direction. So what do I mean by that? You might remember when we were doing the questions from last week, we assumed that the positive XY axis goes to the right and up as the positive directions. And similarly, we're going to assume that the counterclockwise direction is the positive direction when we're doing all our moment calculations, all right? Okay, any questions so far about any of that? No? Okay. Cool. So let's run through kind of a more thorough example. So I'm going to go through a beam example because it'll come up again and again in this course and future courses probably. So this is a simply supported beam where basically you've got supports on two sides of it, and essentially one side has a pin support and one side has a roller support, and these are like mathematical concepts, okay? The idea is that the combination of the pin and the roller support give the minimum amount of unknowns in order to solve this structure using our concept of, it's called equations of equilibrium. Okay, so that was a lot of random shit I just said. Let me break that down as best as I can, okay? So the idea is you've got this one-dimensional beam, right, with length L, and on the left, that pin support, it produces two reactions, okay? Let's call it AY, that's the wrong one. AY and AX. So this is essentially what the support is resisting, okay? So it resists the normal forces, which is through AY, and it resists the tangential forces, all right? So this is the reactions, is what it's reacting towards, okay? So that's AX. But it doesn't resist rotation, okay? So you can see here with this little dot, I'm representing this pin support allows for free rotation, like a hinge, like your elbow or something like that, okay? The roller support, in contrast, resists, let's call that BY, only the normal forces, okay? And not tangential forces, let's do that in a different color. Not tangential forces and not rotation either. It's got the same kind of thing. Okay, so what do I mean by that? If you imagine, let's look at the roller case. If there's some kind of horizontal force that's pushing on it, it just freely rolls without friction. So it doesn't, since it's frictionless, right, like the rolling, it doesn't produce a reaction. It doesn't react in any way, right? Whereas if I push down on it, it will push back. Does that make sense? So I'm pushing on this table, it pushes back onto me, right? And that produces the reaction. And so a roller only produces the vertical or the normal force reaction, not the tangential one. Okay, in contrast to this, a pin support is something that will hold back against horizontal forces as well. Okay, so if I push kind of like diagonally at that, it's going to push back or want to balance out that force, right, and keep it in equilibrium. Does that kind of make sense? Okay, I'm going to try to go through this as slow as I can to explain every part. Okay, so the supports, yeah, there's a few things like regarding these supports, right? So the supports produce these reactions, okay? So, okay, it starts from supports, all right? So the supports to produce reactions, and then these reactions mathematically are unknowns, okay? The things we want to solve for, okay? We want to be able to quantify these things. How do we do that? We use something called equations of equilibrium, which is what I was trying to say before. Okay. And equations of equilibrium is actually what we've kind of looked at a little bit like last week, but not all of them, okay? So that's using Newton's first law of statics. You've got some of the forces in the y direction, some of the forces in the x direction, or any set of forces which are at 90 degrees from each other will work, so normal tangential ones will work. But now we're also we've kind of unlocked this third type, which is using the equilibrium of moments about a given point in order to solve stuff, okay? And this is the tricky one to kind of wrap your head around, so I'll spend as much time as we need to get you guys to wrap your head around this concept, okay? But the idea is that using this, we can kind of solve for these more complex systems. So this is the beam. It's a 1D rigid body. In the previous workshop, we've only talked about particle equilibrium, right? Like I didn't really say that word because I didn't want to jump too far ahead before. But last week, you'll see all of the examples of forces only were particle equilibrium kind of examples. Now we're dealing with 1 and 2D rigid body equilibrium kind of questions, okay? All right, anyway, I'm going to make that stuff smaller because I'm going to scribble a lot on this page. All right, let's keep going. So yeah, you've got the simply supported beam. And let's say that we're going to put a point load on it, okay? So this is like some kind of external force that's vertical. And this will basically induce reactions. We won't really do the horizontal one. The external force is what induces the reactions at the supports. So if you remember the example we covered last week to do with friction, right? If you imagine a box and it's completely still on the ground and nothing's pushing it horizontally, it's not going to produce any friction, right? But if I start moving it, it's going to start reacting with this friction reaction. And friction is a reaction of sorts, okay? Similarly, these supports will not produce any reaction unless we put an action on it, okay? And the action is the external force, or this F force, which I've drawn here, okay? So keep that concept in mind too. All right. Anyway, so let's say that we want to solve for these supports, okay? We want to figure out, AY, BY, and AX, okay? What we're going to do is we have to consider this concept called lines of action. All right, next, which is, I'm going to do this as a highlight. If you imagine all of these unknowns, and also, I guess, the external force, as having an infinite line that runs through where the arrow is drawn, spanning in either direction. This is something called line of action, okay? So that thing, it's bad to do an arrow because it might, okay, anyway, this yellow thing is called a line of action. Okay, and extends infinitely in all directions, okay? Now, after you think of that, we can then understand the concept of a lever arm, okay? So, anyway, so many fucking things to explain at once. It's hard to find the order which everything makes sense in. Okay, we're solving for these reactions, right? AY, BY, AX. We need to implement this equation of equilibrium, the sum of the moments about a point, and set it equal to 0, okay? And let's say we want to figure out By, okay? Now, where we want to take the moments about will be where it cancels out the other unknowns, okay? And that point specifically is here at A, all right? The reason for that is if you look at all of these green lines, right, the lines of action of our unknowns, that's where all but one of the green lines intersects, right? So I'll tell you why that's important in a second. So now if we choose to look at this point A, what you'll find is that we've got the line of action corresponding to that external force F, and we've got the line of action corresponding to our unknown B, that's some distance away from it, okay? And this will allow us to solve for By, okay? So what do I mean? Now we have to consider the concept of lever arm, which is a perpendicular distance from our point of reference, which is A, to these forces, okay? Perpendicular distance. So I'm going to draw that, like so. And, well, this one, let's just call it D. And the lever arm between A to B is just going to be L, the length of the beam, okay? All right, so if I do my calculation for the sum of the moments about a point, we're going to consider that point as A. So that's now where our camera, I guess, like starts, right? We're going to look from there. Is equal to 0. Okay, next, we have to sum all of these moments. Now remember, the moments are equal to a force, the force, multiplied by the lever arm, okay? So let's consider this force first, right? The force is F, and the lever arm is D, right? So that's force times lever arm. However, there's one more thing to consider, and that's direction, okay? So the idea is, about this point, this force will produce a clockwise spin, right? And we know that since we're considering counterclockwise as positive, a clockwise spin will result in a negative moment. Okay, so since it's clockwise, I'm going to do negative. And next we're going to consider, By, which will produce a counterclockwise spin about point A. Okay. So since it's counterclockwise, I'm going to do positive. I'm going to do By as the force, and L is the lever arm, right? Okay, going back to why I chose the point A, if you consider these ones as well, if we wanted to also, I'm just going to do plus, right? If we wanted to also consider AX and AY, we'd get to this point. But then when we're choosing our lever arm, there's zero lever arm, because there's zero distance from the point that we chose and our force, okay? It coincides. So that's why these essentially get deleted when you choose a point to take the moments about that coincides with those unknowns. Does that make sense? Kind of? I saw someone shake their head. Okay, maybe that'll make more sense when we see a question. But the idea is now we've ended up with an equation where 0 equals to something that we know. Say we're given the external force. Say we're given that distance. Say we're given the length. And so we're just left with this one unknown, which we can actually solve for, because the equation to correspond to that one unknown, right? Okay, if that doesn't make sense right now, hopefully it'll make sense in a second when we go through some examples, all right? Okay, so question 1. We've got a simply supported beam, which has a crate on it, and we also have to consider the self-weight of the beam, okay? So let's see what that all looks like. The first thing to note is how we represent things mathematically doesn't always look like the way that it physically is, okay? So if we look at the support on the right, this kind of lines up with what I drew before with a pin support. So the idea is that this support that's holding it is fixed to the ground, and so it's going to resist any vertical loads as well as horizontal loads. And you can see that it has this pin that it spins about, which allows for it to freely rotate without any friction. However, this support on the left, right, is, I guess, more of a rocker support. So it doesn't quite look like, I'm just going to draw the on. It doesn't quite look like the roller that I was talking about before, but the thing is, it doesn't actually really matter because they mathematically behave the same. All right, a rocker and a roller effectively behave the same, and the reason is because a rocker will resist the oh fuck's sake, doesn't work either. Okay, sorry, check the recording is, hello, yeah, that's working. All right, sorry, where was I? Yeah, so the rocker doesn't resist like horizontal translation. It will allow the system to move left and right still, okay? So effectively, it's gonna behave like that. Anyway, all right, so that's all good. Now we understand the supports. We're gonna turn that crate into a single point load, and we're gonna call it P, which will be this. And the self-weight of the beam, we're gonna call W, which is like a uniformly distributed load, which I'll explain a bit more in a second. But yeah, that's gonna be our free body diagram that we're working with for the remainder of this question. Okay, so now we have to convert our masses into forces, right? And we know from the force of gravity is equal to mass times acceleration due to gravity, where we're going to consider acceleration due to gravity as 9.81 meters per second squared, that we can just essentially convert mass to a weight force. Like so. I'm just going to get my notes up on my phone so I don't have to do the calc in my head. All right. So essentially, let's do the point load first. So that's the crate. We're told the crate is 300 kilograms. And we're going to multiply it by 9.81 meters per second squared, giving us this number in newtons. And conventional units for when you're analyzing beams is going to be in kilonewtons and meters, okay? So we're going to convert this into kilonewtons. So 2.943 kilonewtons, all right? So that gives us the point load, essentially. So now we have this. All right, next we're going to do the self-weight of the beam, and we're told that's 50 kilograms per meter of length, all right? So I'll explain that a bit more in a second, but I'm going to include the units for this line of working. We're told it's 50 kilograms per meter, all right? And we're going to multiply that with 9.81 meters per second squared. And you'll see that it's going to result in essentially the same as what we did for P, except it's going to be per meter along the beam. Newtons per meter. And if we want to convert that into kilonewtons per meter, we just divide by 1,000 again. Right? And this gives us something called a distributed load. We'll be talking about this a bit more next week. But this is a distributed load. And the idea is instead of the force being at a single point, like the middle, it's essentially spread out over the whole beam, like this, because it's the self-weight, okay? And we represent it on pen and paper like so, like this kind of rectangular shape that's pointing downwards, okay? Any questions so far about that? No? Okay, so that's the external loads, and we've just, quantified them. Next, we're going to use our equations of equilibrium to solve for the support reactions, okay? And this is usually the first step whenever you don't know the reactions. You have to use the equations of equilibrium. Okay, so let me just bring this, you know what, I'm going to change P into what it was in kilonewtons. So this was 2.943, and W I'll change to 0.4905, just so it's a bit more clear what is known and what's unknown, okay? I'm going to move this, bring it down to our next line of working out. Okay, so basically we're going to draw where well, you don't have to do this every time, but it's just for the sake of learning, where the lines of actions are. of our unknowns, which are here, here, and bx goes sideways like that. All right? So now we choose a point which coincides with all but one of the lines, and then we can work out that line. Okay, so in my case, in my working, I've decided to choose point B. So here's our new point of reference, and so we can essentially ignore those two lines now, the ones that coincide directly with it. Okay. I just got some eyebrow raises. Does that kind of make sense? Yeah.
Would one line of action be where the force is going down?
Yes, you're right. So there are going to be lines of actions, but specifically in green, what I've highlighted are the lines of actions for our unknowns, the ones we don't know.
Oh, okay.
So we know 2.943 for P, so we don't need to consider that. But yeah, it's a good thought, and we can keep that in mind for the next step. Yeah. Just as a thought experiment, right? There's one other point that we can choose, right? In order, like instead of B, we could have chosen to take the moments about A instead, right? In which case we're looking from here, so this is where the camera starts. This line and this line coincide with that point, and in which case we would be solving for By instead, okay? But instead, and how I've done the working out, is we've chosen point B, okay? Since we've chosen point B, we're going to be working out the unknown AY, okay? All right, so now we have to sum all of these forces, okay? So let's start with AY. So AY, and here's our camera, is producing a clockwise spin about around B, right? So that gives us negative AY, right? And now we have to consider the lever arm. The lever arm is going to be 2.4 meters plus 1.2 meters, right? Which I'll just write as 3.6. Let me just do this. That's 3.6 meters. Okay. Okay, next, we're going to consider, like you were saying earlier, this line of action for the external force. Okay. So the force is 2.943. It produces a counterclockwise spin about point B, and so it's going to be positive. And the lever arm, there's so many words to say, the lever arm is 1.2 meters away, right? All right, question. Have we considered every single force now? No, we haven't, because we haven't accounted for the distributed load, right, the self weight of the beam. So how do we do that? Okay, so let me just redraw this so I don't crowd that picture above. So you've got all this, you've got the support conditions as per the previous diagram, and we've got this, sometimes I draw the uniformly distributed load as that, so these downwards arrows is the same as doing it like that. That's just the lazy way of doing it essentially, right? And let's just forget about this point load for a second, right? How do we figure out what the lever arm is from any given point of reference, like A or B, okay? The idea is that you can convert this distributed load into an equivalent point load by adding up all of the downwards force that it produces into a single point, okay? So the idea is that, let's call that F or something, and this was W, all right? W was 0.405, oh, sorry, no, it wasn't, 0.4905. This is in kilonewtons per meter, okay? And the length of the beam was 3.6 meters, right? So what is the equivalent downwards force produced by F, okay? And the answer is you do W multiplied by L. So you do 3.6, which is how many meters that distributed load acts over, multiplied by how heavy it is per meter, right? That kind of makes sense, because now we've just got the net downwards force produced by it, right? And in terms of a uniformly distributed load, and we'll talk about this more next week, because the self-weight is uniform, so it's as heavy on the left side of the beam as it is on the right side of the beam, you actually can consider the uniformly distributed load as this kind of rectangular shape. So actually, this is like kind of bad for learning. They're doing this crap. Yeah, it's this like rectangular shape, and we want to find kind of like the center of gravity, all right? And you can see just visually that the center of gravity is halfway in the middle, okay? For a uniformly distributed load. In the next workshop, we'll talk about triangularly distributed load, trapezoidally distributed loads, etc., which get more complicated. But for now, let's just focus on a rectangularly distributed load or uniformly distributed load, okay? All right, so I'm going to delete that for a second because I'll basically just do that again, but on this other graph that I've drawn, or this other free body diagram that I've drawn. Okay, point is, the blue, what I've drawn in blue, the uniformly distributed load, will actually have a lever arm, which is in the middle of the beam, okay? So, what we're going to do is, because that equivalent point load is going to be pointing downwards, right? It's also going to produce a counterclockwise spin about point B. So we're going to do positive, sorry, not BY, what am I doing? Positive, we're going to do WL, right? So that is the magnitude of the force that's pointing downwards. And we're going to multiply that by the lever arm, which is how far away it is from B, which is going to be 3.6 meters divided by 2. Right? So that gives us the lever arm as so, as wrong. Okay, and we know what this is, we know what this is. We don't know what AY is, okay? So actually what I'm going to do, sorry, I know you guys might be copying down this, but I'm really running out of space, is I'm going to replace W and L with the actual numbers. So W was 0.4905 and L was, it acts over 3.6 meters, right? Okay, now we've just got AY, which is our unknown, and when we move that to the other side and divide accordingly, we get 1.8639. So now we've actually managed to figure out this unknown, right? Which is great. So now we're left with only BY and BX, okay? In terms of unknowns, right? I promise, for those of you who are already like across these concepts, I'm going to speed up for the following questions. It's just I want to go slow so that we all kind of are on the same page for this first question, all right? All right, so at this point, you might be thinking, holy crap, that took so long. Well, one, because we're going slow, but like, do I now need to take the moments about A in order to find BY? You know what I'm saying? And the answer is no, because we only have one unknown in the vertical direction and one unknown in the horizontal direction left. So we can use the easier equations of equilibrium formulas, such as some of the forces in the y direction and some of the forces in the x direction, in order to solve for these remaining unknowns, right? So in the vertical direction, we're just looking at the upwards arrows as positive, minus the downwards arrows are negative. That's it. Like it's very fast from this point, right? So we go AY plus BY minus W, which is the distributed load, multiplied by 3.6, which is how long the beam is, which is how long the distance which the weight is acting. And we also minus P, which is, yeah, basically, sorry, I'm being a bit inconsistent with my notation, but W was 0.4905 and P was 2.943, right? And we also know what AY is. It was that previous answer. So now we're just left with BY, right? And BY, when we solve for it, is 2.8449 kilonewtons, okay? So now we know what BY is, okay? Now BX, it's a horizontal reaction, right? But the idea is we don't have any horizontal forces externally on the beam. So it's actually going to be 0. But we can prove that it's 0 like anyway by taking the sum of the forces, right? The idea is your sum of the forces is equal to 0, which is equal to our unknown BX, right? Which is literally the only arrow pointing to the right at all. and so therefore bx is equal to 0. But this is the same as, like, this is the same kind of concept as having a box on the ground and you're considering the friction, right? But there's no horizontal push on it, right? Since there's no horizontal push on it, there's not going to be a friction pushing back at it, right? So anyway, that's kind of one way that you can think of horizontal reactions being 0. Okay, so that is the first question done, and I'll give you guys a break. But before that, do you guys have any questions about how that all works? That's the slowest I'll go, I promise. I'll speed up after this. All right.
How do you calculate distributive force again?
Sorry, can you say that again?
How do you calculate distributive force? Wait.
I think I understand what you're saying. I'll draw it out again. So we've got the beam. Right, and say you've got a uniformly distributed load, as so. W is okay, I'm just going to do a nice round number. This is not the same example as before. 1 kilonewton per meter, right? Actually, no, it's actually easier to see this if I make this like 2 or something, right? Let's say the length is 3 meters, okay? The equivalent point load going down is equal to 6 kilonewtons. Does that make sense? So it's per meter multiplied by the amount of meters it acts over. That gives you the equivalent point load that acts down. Yep. Okay. Again, we'll do a break. Start again at 10:03. Okay. Hi, you got a question?
Yeah.
Yes, what's up?
So, first of all, with the lines of action,
Yes.
so you pick the point to rotate about, which has the most lines of action going through it.
Yes. It's not actually about how many lines of action are going through it. It's about how many are remaining that aren't going through it.
Okay.
Okay, so I'll show what I mean. Okay. So here's the simple example that we've been seeing, right? Basically, we'll draw the reactions. AY, AX, BY, right? Boom, boom, boom.
Yeah.
If you pick point A, you delete this and that.
Yeah.
Yeah, you've just got 1, right? Okay. More complicated example. I'm gonna do a frame that's got a piece that's got a pin here and here. So this one's up on like a higher surface or something like that. You'll see that this and this will be like AX, AY, BX, BY. Boom, 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 boom. What you'll find, I'm just going to keep drawing further, is no matter what point you pick, you're not going to be able to solve it using equations of equilibrium. The reason is if you pick point A, you still have 2 unknowns that you can't solve for.
So you can only solve for it when there's only 1
Remaining.
Yes. And I guess intuitively.
Oh, sorry. You need 2 fingers.
Oh, okay.
I have like a move
yeah.
detection thing. Yeah.
Like
it ignores one
intuitively, it
finger.
makes sense that like if you pick this point, then you don't have to solve for AX. But like if you picked the point like at B, wouldn't that like you would still have 2 lines of action going through it? Like I don't.
Okay, so if we delete, so we pick point B.
Yeah.
It still deletes AX because a line of action isn't localized into this point.
Okay.
It extends infinitely in both directions.
So you could also pick BY and it would still be the same.
Yeah, because if I pick BY, it deletes here and here.
Okay.
Yeah, it still deletes the AX line.
So with the first example that we did, was it just because there was like another force that you didn't pick BY? I don't remember.
Oh, this
I
very
don't know
first
what that
thing?
was. Yeah.
Yeah, this is actually like kind of almost worse to explain the concept than having numbers associated with it because we actually know what F is.
Yeah.
Yeah. So that's why I tried to do it in yellow to kind of represent that it's a line of action that we know, so we don't have to consider it when we're...
So if you picked like point B for this example,
Mhm.
you would still be able to solve it?
Yes.
Okay.
So, for example, we go here, here. We pick point B. We've deleted the horizontal one, and we deleted this one. Now our lever arm between the points stays the same, but our lever arm from F to B, let's call that distance A. It's the lever arm A.
Okay.
So it'll just be,
Makes sense.
and A is equal to L minus D. That's just a fun fact. That doesn't really have anything to do with, yeah. Do you know what I'm saying?
Like, so this is only solvable because like there's no horizontal force, so
Yeah.
AX is equal to 0.
Yeah.
But if there was a horizontal force, then
So
I guess it would still be possible. It would just
yes,
be
it'd be
more
solvable. Exactly.
Yeah.
So let's just
Okay.
say there's a horizontal force for whatever reason that's applied on this beam.
Yeah.
Say there's like little plates that you can like pull with rope or something like
Yeah.
that going to the side. That horizontal force is absorbed 100% into AX. Okay. The reason why it's called a simply supported beam, right, is because in contrast to a simple beam, if you have something like this, where's pin? This is completely solvable if we only consider vertical forces, right? But as soon as we have something, let's just say horizontal or diagonal force, we've got line of action, boom, 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 right, like that.
Yep.
Problem now is, let's just say we choose to take that, right? Oh, sorry, okay. What you'll find is you'll be able to solve AY at BY, okay?
Yeah.
But what you won't be able to solve is because these two reactions are coinciding with each other, all you have to be able to solve it, because they're coinciding with each other, there's no point you can pick where the sum of the moments leaves you with only one of them. And so when you try to do sum of the forces is equal to, the sum of the force in the x direction is equal to 0, you're stuck with AX and BX, and you cannot figure out the proportion that goes into A and goes into B.
Yeah. Okay.
This is called statically indeterminate. The previous cases which we talked about were statically determinate. Indeterminate being you can't figure it out. If you're doing civil, which you might not be, in civil engineering, there'll be a course later that lets you figure out these things. It's called methods of structural analysis or something like that. Yeah, and there's all these little tricks that you can implement. They give you additional equations that you can use to solve. But in this course, we only deal with equations of equilibrium, so it'll always be solvable
Okay.
using just this.
Sorry, I had a few questions about
Yep.
the design project as well.
Oh, sure.
Sorry, I'm taking a long time.
No, that's all right. Yep.
To what extent do I need to pad out my report? Like, is it better to have like a concise 9-page report or a more detailed 20-page? Like, do you know who's marking?
This is I don't know who's marking, but it's not me.
Okay.
But also, this is the first time the project's been run actually.
Okay.
So I don't know what a good report looks like.
Okay.
But maybe like in later weeks when you guys are like near the finish line for it, you can come to me and I can have a whiz through your report and
Okay.
give you a bit of feedback or something like that.
I think that's all.
Yeah, because right now I haven't done the
Yeah.
I haven't done the assignment either. It's the first time anyone's done the assignment, so I can't tell you what a good report looks like. Yeah, no worries. Hey, what's up?
I can
Yeah.
come in.
No, let's yeah.
About the lines of action as well.
Yep.
Because I'm just like, you say you chose point B, so then you got rid of these two lines.
Yes.
And then that was the only one left.
Yes.
If you had them both as pin loads, would you have to do the moment equals 0 for both of them?
Nah. So what you'll find, okay, so let's say they're both pin, and let's say we have
Or is
this
that
like,
the one where you can't figure it out?
oh, you can figure it out actually. So what you'll find is if you go down this rabbit hole, is you got pin there and there, and then you've got these two horizontal reactions which have like the coinciding line of action. What will happen is if you take the sum of moments about let's say B, you'll delete both of these horizontal ones and that one. So you can actually figure out AY.
Oh.
Let's say you do that, and let's say you do the sum of the forces in the vertical direction is equal to whatever, and then you can actually figure out BY.
So it's just exactly the same.
Except now you've got these two horizontal reactions that you can't distinguish between, because since they coincide as lines, there's no point that you can pick which will distinguish them with the moment equilibrium.
So you can only figure out the x coordinate.
Yes.
Okay.
Yes.
Okay. Okay. But why did we choose B? Because if you chose A, technically
You can figure
That
out BY
would-
instead.
that would disappear as well.
Yes. So if you, okay, sorry. If instead of choosing B, you choose the point A, what will happen instead is you're figuring out BY, which you can do, and then you'll
So
just,
even though at point A only has that, you can still get rid of the horizontal
yes,
one.
yeah.
At
Any
that
lines that cross over that point, you can just ignore.
So we could have just figured out BY here. and
Yeah,
AY there.
yeah.
That wouldn't have
There's
changed
no,
anything.
like, it's completely arbitrary which path you go down. It ends up, have you seen that meme that's like got the cow? It's like a cow, and then there's like, thank you. And then you got two paths, and it leads to the same point. That's basically what you're doing. You
okay.
choose like point A, or to point B, it leads to the same end result.
Easy.
It's arbitrary, the path that you take. Yeah.
It's a very good experiment.
Thank you. All right. Okay. Sorry, that was a bit of a longer break than expected, but hopefully everyone's back. I haven't been keeping track. Maybe someone was out in the bathroom. But yeah, I'm just going to continue anyway. Okay. So this is a question that I actually originally got wrong, and then I realized how to fix it. So yeah, let me show you the question first. So we've got a trailer that's towed, and there's a force that's applied here of 500 newtons on the ball of the trailer hitch. Determine the moment of this force about point O. So that's over here. Okay. So the reason why it was a bit confusing to me at first is because whether you apply the force like so, where it touches the surface of the ball, or the middle of the ball, which is what I actually thought the question was originally, does actually make a difference for moment equilibrium. Now, it doesn't make, like in the previous week, right? You might have seen a ball or something, and then you've got these forces that are applied. Say this is particle equilibrium. You got these forces that are applied, and as long as they coincide with the middle, right? You don't have any moments, and you can actually still figure out. Everything. Like, it's the same force equilibrium. But the difference with moments is where the force is applied exactly makes a big difference for your lever arms. Okay, so what do I mean? The difference is this distance here. Actually, I'm going to draw it the other way around. We know that this is 32 millimeters radius, and so that difference in the horizontal component of it and the vertical component of it will affect the lever arm, which we take about O. Okay. All right. So there's basically two parts to this question, right? There's the part where we have to split up the force into its component, its X and Y component, and then there's a part where we consider the lever arm or the geometry of the problem as well. Okay. So I'm going to split the force into the horizontal and vertical components first, and I'll explain why. So if you consider the line of action of this force relative to O, you'll find that the perpendicular distance looks something like this, right? And you'll find this is a pain in the ass to find the geometry. You probably could do it, but I wouldn't recommend doing it, right? What's actually easier sometimes is to consider this force as its horizontal and vertical components instead, in which case you have much easier lines of actions to deal with, and we're already given essentially the perpendicular distances, right? So sometimes that can be advantageous to you. And that's the approach that we're going to do with this question, all right? Okay, so yeah, I've basically just redrawn what we see above, but removed a bunch of fluff. Oops, I don't know why that line's extending out. Okay, so it looks something like this, and that's the geometry. But we're going to break the force into its horizontal and vertical components first, all right? And so that's just a matter of doing what we did last workshop, which is considering trigonometry and the adjacent side, the opposite side, etc. So, yep, that's the horizontal force going to the left, and this is the vertical force going downwards. Yeah? Okay, so that is all good. Okay, before we can do the resultant moment, we have to basically figure out this precise geometry, okay? So, this distance of the radius is the hypotenuse of this right angle triangle, like here. So it's 32. And we basically have to figure out the side lengths, A and B, okay? So the idea is that we can use our understanding that cosine is adjacent over hypotenuse, right, which is that, and rearrange it to figure out that adjacent side, which we're calling A, okay? And so we go 32 cosine 30 on our calculator. That gives us that this distance is 27.71 millimeters, okay? And for the opposite side, we do a similar thing. And this time we're considering the opposite side length as B, like that. And we go 32 sine 30, which gives us 16. So this is 16, okay? So now that we've got this kind of like microscopic geometry, we're going to see how it plays into the bigger picture, okay? So basically the horizontal component, I'm gonna erase this 32 radius thing because it's actually not important anymore. The idea is that the horizontal component is how far from the middle of that ball over to where the force starts, and that was 16. So that's equal to B, which is 16. And the vertical component is the ball to the line of action of the horizontal. So let's do that in terms of lines of action. So that's A, which is equal to, what did I say it was? 27.71 millimeters, okay? Cool. So now we can actually figure out the lever arm for real. So the lever arm where we care about is from point O to where the force is. So we care about that distance, and then we'll also care about from here to there, okay? So, one sec. I'm gonna move this. Like so. Oh no, it's a bad spot. Maybe here. Okay, so let's consider the vertical force first, so Fy. So Fy, its lever arm is going to be this purple distance here. So we know that the larger distance is 275, and we're going to subtract off B, which was 16, okay? So that is going to be 275 minus 16. All right, and the reason it's positive is because it's generating a counterclockwise spin about O, right? If we look at Fx, which goes that way, it's generating a counterclockwise spin as well. So we're going to add these two induced moments together, okay? So do Fx. Now this distance is going to be, instead of one subtracted from the other, it's going to be additive, right? Because we're going to add 38 millimeters onto 27.71, which was A, right? So now this time it's going to be 27.71 plus 38, right? And we've worked out Fy and Fx in the previous steps. So Fy was this, Fx was this. All right, so now we can just punch this all in the calculator and get this. Yeah, so what we're doing isn't exactly figuring out a reaction we're figuring out the resultant moment, and the resultant moment, I think I spoke to you briefly before the class, is just grouping all of the moments together relative to a certain point. It's equal and opposite to what an actual reaction would be. Does that make sense? Okay. All right. Any questions so far? I see people copying this down, so I don't want to like scroll to the next page, but then I also see people not copying it down, so I might just move on. You know what I'll do as a compromise? I'll show you the QR code again, and what you can do is, if you need to copy it down, it'll be up on the, it'll be in my drive, so you can keep copying it down or whatever. Okay, cool. So now we'll move on to the next question, yeah? All right, so question 3. Yeah, basically we've got, it says a block. Okay, so that's the ground, this is a block. A block is placed under the head of a hammer claw as shown. A block placed under the head of a hammer claw as shown greatly facilitates the extraction of a nail. If a 200 Newton pull on the handle is required to pull the nail, so that's that going diagonal, calculate the tension in the nail, right, which we're going to do as that. Or did I do it? Sorry, wrong way. I'll explain why that's pointing down in a second. And the magnitude of A force, and the magnitude A of the force exerted by the hammerhead on the block. So in other words, a reaction. The contacting surfaces at A are sufficiently rough to prevent slipping. Okay, so there's a few things to explain about how this system's supported before we kind of dive into it. The first thing to realize is that what kind of support is actually happening here, right? And the answer is, the answer lies in how we translate a physical system into like a mathematical representation, okay? And so what do I mean by that? Basically, if you think about a simply supported beam, beams in real life all the time aren't literally supported with this little triangle thing with a little pin going through it that allows rotation. Beams in real life a lot of the time that are simply supported look something like this, right? So you imagine like a plank of wood that's, say, bridging between two of the tables in this room, right? So there's like a suspended gap or something like that. This can actually be modeled as a pin, like here to here, okay? And the reason for that is that it fulfills all the requirements of a pin. So a pin support basically resists vertical reactions. Let's not talk about the horizontal reactions, like yes, they technically do, but this beam, let's just consider the vertical loads on it only. So let's ignore these horizontal ones. So it resists vertical reactions, for one, and then two, when it bends, it allows for free rotation at the hinge. So here and here, it allows for the beam to flex, basically, at those points, okay? So why do I bring that up? Oh, actually, no, some of you guys might want to copy that. Why do I bring that up? Well, it's because this essentially behaves a very similar way. We've got essentially a pin here that's resisting, that's point A, right? That's resisting vertical and horizontal translation, as well as allowing for free rotation. So this is basically a pin because the hammer is free to rotate about that point. Okay, and now the tension in the nail. So if you imagine this nail and think about the equilibrium, right? It's stuck into the ground, and if we pull on it to move it, basically, the ground, and in fact the friction between the nail and the ground, actually wants to react, right? We call that T, tension. It wants to react the other way to stay in equilibrium, in other words, to prevent the moving, okay? And so that's why we point the unknown T downwards, okay? Actually, if you choose the wrong direction for a reaction, it doesn't particularly matter. You'll see that in this question for AX, okay? And the reason is you're just going to get a negative number. And a negative force vector just implies to you that, in fact, the force is going the other way. Okay, so I'll show you what that looks like in a second. All right, so that's my explanation of the reactions, right? Okay, so next we look at the free body diagram of the system, and the first thing to note is how we've treated the angles, right? So we're told that the hammer is angled at 20 degrees, like shown, but you can see from your understanding of I guess angles and how 90-degree angles work, right? That's a right angle, is that this also has to be 20 degrees, right? Because the hammer's straight, right? So that's 20 degrees. And the other thing to note is sometimes it's important to understand our forces relative to the horizontal axis, right? Our x coordinate. And so you can see if we consider this as 90 degrees, then this is also that 20 degrees, right? On that plane. Anyway. Yeah, these are all like kind of equivalent angles, right? And so what I've done in my free body diagram is I've just drawn 20 degrees everywhere. That might be useful. Okay. So now the next question is essentially what path do we go down in terms of our equations of equilibrium in order to solve for these support reactions, right? So you've got some of the forces in the x direction or y direction or the moments. And for this particular example, it's fine to go to do one or the other of these first. You just can't do some of the forces in the y direction first. And the reason is because if you think of the unknowns, there's too many in the y direction to solve at the moment. But what you can do is you can actually still do the sum of the forces in the x direction first. And the reason is because the only unknown ax, right, is independent of the other reactions. So in this particular question, the way that I've solved it is done the sum of the forces in the x direction first, before some of the moments, okay? Did that make any sense? Maybe not. That wasn't my cleanest explanation. Okay, you'll see what I mean. Anyway, point is, you could have done this first, or you could have done this first. Either order is fine. But you need to do this, you need to do this before you do this. That's what I'm trying to say. Okay, so as long as you do the sum of the moments before you do the sum of the forces in the y direction, you can actually solve this. All right. Sum of the forces in the x direction. So we're going to work out that unknown, which is the horizontal component of the reaction A first. Okay, so let's look at all of the horizontal forces, right? We've got our reaction, AX, pointing to the right, and we've also got the horizontal component of our diagonal, right? Which is going to be 200 cosine 20, right? And what you can see is that when you rearrange for AX, you'll notice that this actually gives us a negative. And what I was trying to say before is that this negative number implies that our actual unknown that I've assumed is pointing to the right is actually pointing to the left. Okay, but we're just going to leave it as a negative number for now. Okay. So that is our first unknown solved. Okay, now at this stage, we're going to try to resolve our two vertical reactions, right? T and AY. Okay, and we look at the lines of action. These unknowns, right? Let's do it in a smaller size. This one and this one, yeah? And so we have to pick a point. We have to pick a point that allows us to solve for the other point. Now, we want to look at the geometry as well as, basically the geometry, right? What is going to make our lives the least annoying for this particular example in order to write down this equation? And if you choose to take the sum of the forces about T, what you'll find... Okay, actually wait, let me show you the question first, right? What you'll find is that, firstly, I guess T would start here. So that's T. What you'll struggle to find is this diagonal arrow, right? How far away is it from T? And you'll have to do some jumping around and stuff like that with with the geometry, but that's a pain in the ass. My point is, if we take the sum of the forces about A, what we're going to find is we actually already know the geometry difference between that are there. I didn't draw that very well, but yeah, we know the geometry difference is 200 mil, and we also know the difference between this point to this point, right? The lever arm, I should say. Geometry difference, what the fuck am I saying? All right, so what we're gonna do is we'll do T, right, which is this force, and the lever arm, the line of action is in green. The lever arm is gonna be 50 mil, and that's going counterclockwise relative to A, so it's positive. And then we'll also consider the 200 newtons, right, which I'll do in yellow as a line of action. And we know that lever arm is 200 mil, right? So we'll go 200 times 200 mil, right? So 200 newtons times 200 mil. Yeah, there's no need to split this into its vertical and horizontal component. In fact, it'll be more annoying to calculate for this particular case because we already are given that perpendicular distance already as 200 mil. Okay, so that gives us T is 800 newtons, right? All right, now we'll do the sum of the forces in the y direction, all right? Because we've resolved what T is, so now we've just got one unknown going vertically, right? We've got AY plus TY minus, minus T, because T was pointing down, plus 200 sine 20. Right, so that was the vertical component of, that's 200 sine 20. That's the vertical component of the 200 Newton force, is that one. Okay? And that gives us, once we solve for it, is AY is equal to 731.6 newtons. All right, so now we've got all three supports solved, okay? Now, going back to the actual question, it wants us to find all of those, but also specifically it says it wants the magnitude of the force exerted by the hammer onto the block, right? And so remember, we had some kind of value for AY was equal to something. We had AX was equal to some negative number. What I'm going to do is I'm going to flip that now so that AX is pointing to the left and is a positive number. Okay. And what we will actually want to find is, because we're given the vertical component and the horizontal component of this reaction, we want the diagonal net force, right? And so going back to our methods that we discussed last week, we can use Pythagoras' formula in order to find that diagonal, or the hypotenuse, which gives us 755.35 newtons, right? And the other thing, in terms of expressing these forces, oh yeah?
Does it matter if you flip them or not?
It matters. It'll give you the same magnitude, but remember the direction, which is represented by this angle, will kind of be wrong, if that makes sense. So I'll come back to that, all right? So we want to figure out theta, which is that angle relative to the horizontal, right? And we can use that using tan inverse rise over run, which is this, right? And this is an angle, and then this is a force, right, which we discussed last week, is a way to represent like a force in general, right? Like this is a way to represent a force. But going back to what you were saying, if we have like a force that's like that, and then that angle is, whatever, let's call it FA, right? That is not the same as that, right? That is not the same as that, because when we say an angle, we have to say it relative to a direction. So the way that you would word this is, this I guess is the angle inclined from the negative x-axis. Do you know what I'm saying? Whereas this example is not the same because this is inclined from the positive x-axis, right? So it gives you a different direction for the force.
But why did
Yeah.
you make it from? Why did you want the answer from the negative x-axis? If like it was like a ledge, right? So wouldn't it be your positive x-axis?
Oh, okay. So it's because, okay, you've got you got that ledge, right? So that's the physical geometry, and you've got this hammer, right? And you got that force and all that. No, and then it's kind of complicated. Okay, let's not say a hammer. Let's say there's some kind of force pushing diagonally onto that block, down and to the right. So I'm pushing that hammer down. The block, wait, let me just think about this real quick. Yes, I think that's how it works. The block is pushing back up and to the left. So it's going to the left. Does that make sense? Yeah.
The reaction force.
Yeah. We're concerned about the reaction, yeah. Yeah. Yep.
Sorry, when you were figuring out the f of x, you didn't include the, like, you then later in the moment decided to use the t with its x, wasn't it? But then you didn't.
Are you talking about this step?
Yeah, but then you use t50 as for the moment, but isn't t50 like
Oh,
like when you figure out the moment, you use the x coordinate of the tension and then also like a diagonal. That wasn't on the x.
oh, okay. Okay, this is too messy to draw on. I think I kind of see what you're saying. Okay, you got a hammer. I'm gonna draw it like this or something. You got this, right? This is point A, which is what we're taking everything about. You've got, I think that was the direction of the arrow. No, it was the other way. You've got some force, 200 newtons, right? And then you've got the tension, right? T. Okay, so everything's relative to point A, yeah? Let's draw the lines of action, like that, for the known one, and like that for the unknown one, right? All that matters in, like, when you're working out the lever arms is the perpendicular distance to those lines of action. Okay, so what do I mean by that? From A to T, from A to T, it was 50 mil, because that's the perpendicular distance. I'll draw like a right angle. But from A to 200, that's the perpendicular distance, and that distance was 200 mil. Is that kind of what you're asking, or a little bit different?
Yeah, and then why didn't you use the t when you were figuring out what the forces in the x?
Oh, I think I see what you're saying. It's because T is purely vertical.
Yeah, that's
There's no horizontal component when we're taking the sum of the forces like this. No, that's all right. It's a very confusing looking question, I think. Yeah. Any other questions for now? Okay, let's do the last question. This one's a bit of a doozy. So this is from the civil questions, which most of my questions that I go through are actually from the mech or the mining school. They use the same pool of questions because I think it's a little bit easier to understand. The civil questions, some of the questions can get very evil. Okay, so there's basically a trick to this. I'll explain what it is. So we're showing some kind of steel structure, and it's pinned at the base, right? So we've got kind of this pin thing, and then it looks like that and that. And there's some external loads, let's call them, that are happening, right? So we've got a point load of 60 kilonewtons, but we've also got this thing which we haven't seen before yet, which is a point moment. Okay, so it's just a moment applied at a point. You can use your imagination in terms of what this physically looks like, but let's just say, for example, that this steel structure is actually connected to another steel member that's running in and out of the page, and let's just pretend that steel member is in torsion. Okay, so it's twisting. So let's say that the steel member is twisting counterclockwise. This will induce a point moment over here. Okay. Okay, so if this structure was, as you see right here, it's actually unstable, right? Because this whole thing would topple over and collapse. What we've got is a cable, right, that goes this way, and it's in tension, okay? So the way that cables work essentially is that if it's in tension, it'll do something. If it's in compression, it essentially won't do anything. It'll just be in slack, right? So this whole system wouldn't work if the external loads looked like this instead, where the whole thing like collapses to the left. You can imagine it'll look like this and the cable gets all like stringy. Do you know what I'm saying? Anyway, so this is just trying to get your head around how the structure actually behaves, all right, before we dive into the calculations. But yeah, does anyone have any questions about this setup first? Okay, so it's a bit unusual. It's not exactly as simply supported beam. All right, so another thing you might notice about this is that we've got the Pythagorean triple, which will appear again. And yeah, so I'll just show you what the free body diagram looks like first, okay? It will look something like this. And what we can do is that diagonal, which is in tension T, we can actually split that up into its horizontal and vertical components. And this will be useful because when we're finding, you know, our lever arms, like it's more obvious the geometry, stuff like that, okay? So that's the first thing. Okay, the next question is, just trying to figure out the color coordination of what I'm doing. This is going to be purple. This is going to be green. I've been doing on the unknowns, right? Okay. So why have I done this in different colors? Actually, before we split the cable up, these are actually our unknowns, all right? Do you see how, okay. Do you see how if I pick the point A, right, we can actually solve this, right? Because we're left with one unknown, which is the tension T, okay? But if I decided to split that unknown into its vertical and horizontal component, if we picked point A, like on paper, we've actually got two unknowns now. We've made more unknowns and more problems for ourselves, right, on paper. But the reality is that when you do this, you can still solve it. And the reason for that is because these horizontal and vertical components are actually still related to each other through that geometry. So it's actually still solvable. All right, so we're going to go through the working and you'll see what I mean. Okay, so if I take the sum of the moments about A, right, which is here, we can consider this force, right, which is the horizontal force in tension, right, so here, which is 3/5t, which is from our Pythagorean triple ratio. And it's got a lever arm of 3, which is here to here, okay? It's positive because it's producing this counterclockwise spin. All right, next we've got, Next we've got 4/5, which is the vertical component, and its lever arm is 1, right? So that's there to there. And it produces a counterclockwise spin as well, so it's positive. Okay. Next is 60, which goes clockwise, so it's got negative, and it's got a lever arm of 1, okay? So everything makes sense so far. Now the last thing is, how do we treat this point moment, all right? And the answer is that a point moment, no matter where your reference point is, will always just be something that you add or subtract when you're considering the equilibrium of the whole structure, okay? So that 30, specifically it's negative because it's going clockwise, right? So since it's going clockwise, it's going to be negative and therefore subtracted. If I decide to take the sum of the moments at point A, or the sum of the moments, let's say at point T for whatever reason. In our like equation that we write out, it's always going to be a negative 30. Okay, that's how we treat a point moment. This will be more complicated when I tell you about how beams and stuff work next week. All right, but yeah, just consider this for now, like the internal forces of beams next week. All right, so now we've got an expression which represents our moment equilibrium at A for this structure. And what you'll find, as I was trying to say before, both of these terms is actually the same unknown, right? It's the same unknown t, right? So when you solve it algebraically, you've only got one unknown, all right? So that's why I drew that in purple instead of green or whatever for these lines of action, because you can actually work it out. All right, so now we have t. That's done. All right. Now we're going to consider the force equilibrium going in the y and the x direction. So in terms of y, we've got AY, which is the unknown reaction. We've got the vertical component of the tension force, which is pointing down, right? And we've worked out t now, so we're allowed to, solve as is. And we're going to subtract 60, which is the point light going down. And for our force equilibrium, we actually completely ignore the point moments. That's the other thing to note. So for point moments, in equilibrium equations, we add or subtract it no matter where it is. This is the equilibrium of the whole structure. I want to emphasize that because, again, it'll just get more complicated next week. And for force equilibriums, we completely ignore the point moment, okay? That's how we treat it. Okay, and then that gives us AY because we've only got one unknown in that equation. So now we've got AY. And then lastly, AX. Now, in the previous examples for like beams and stuff like that, you've seen that, let's say a simply supported beam, right? You've seen that this horizontal reaction hasn't done anything. And that's because we haven't had a horizontal external load for the question in, like, say, question 1. But once you have a horizontal component, like the horizontal component of the tension force, we will actually have this reaction do something, okay? So that's this here. So now we actually have to solve it, and that gives us a horizontal reaction of 20.8 kilonewtons, okay? So now we've figured out all of the reactions, and yeah, that's it. Okay, any questions so far? I'm going to leave this up on the screen. That brings me to the end of this workshop, so I'm going to stop the recording, but you're more than welcome to come up the front if you have further questions.